let's learn about wave motion. Now, wave motion can be related to simple harmonic motion in the case of sinusoidal waves, but there are other types of waves too. Wave motion is a little more general than that, but we'll talk about sinusoidal waves in the next video. Right now we'll be a little more general. So let's first think about wave motion by considering a pebble dropped into a pond. If you've ever dropped a rock into water, you notice that waves spread outward from that initial source, from that initial disturbance of the rock. And what is happening is that the disturbance, that motion of the water, is propagating outward, but not the water itself. So when you see a wave traveling through the water, it's not a chunk of water that's moving. It is a disturbance caused by a source. It's kind of like a bump that the rock gives to the water. The rock is bumping the water nearby it. And that water bumps the water next to it. That water bumps the water next to it. And that bump or that disturbance gets propagated outward. So you don't have a chunk of water going from disturbance outward. You have a push that's getting transferred. So this is true of all wave motion. In the case of sound, this is interesting to think about. Sound waves are a push or a bump given by some source. In the case right now, what's happening is that my throat, my larynx, is giving the air molecules close to it a push. So every time I speak, it's pushing the air molecules close to it. Those molecules bump their neighbors, those bump their neighbors, they bump their neighbors, and it goes all the way to the microphone in my phone that I'm filming this on. It bumps the microphone, which causes an electrical signal to get recorded by the phone. And then later on when you watch this video, there's a little speaker. Well, you're listening to it somehow with some kind of speaker. I don't know whether it's on your phone or computer, stereo, headphones. That speaker pushes air, it bumps the air. That bumps the air molecules next to it, bumps the air molecules next to it, all the way down the line until that bump hits your eardrum. And that bump on your eardrum sends an electrical impulse to your brain that interprets that sound. Okay, so these examples of waves that I've talked about, a water wave, a sound wave, these are all examples of what we call mechanical waves in nature. A mechanical wave is a wave that travels through some medium. It needs a material, whether it's water or air in the case of sound, or it could be a wave on a string. It could be a seismic wave traveling through the Earth's surface. All these types of waves travel through a material. That's to distinguish these from electromagnetic waves or gravitational waves. Those don't require a medium, so they're not considered mechanical waves. But in Physics 6, we're just going to look at mechanical waves. In Physics 7, you'll learn about electromagnetic waves. So mechanical waves require some source of disturbance, a rock dropped in a pond, a larynx oscillating back and forth. They require a medium that can be disturbed, water, air, something. And there needs to be a mechanism by which adjacent portions of the medium can influence each other. That just means that the air molecules are bumping their neighbors, the water molecules are bumping their neighbors, something like that. So waves carry motion. They carry energy, they carry momentum, but they don't carry matter. When I speak to you, there's not a chunk of air from my lungs going straight to your ears. That would be kind of gross if that was the case. There is a little bit of a puff of air, and that's why during quarantine times we gotta wear masks when we're around people. But I can speak and people can hear me from far away. That doesn't mean that a chunk of air is traveling from my lungs 100 feet away to their ears. It means that air molecules are all bumping their neighbors and carrying this motion down the line. Now we can classify waves as being either transverse or longitudinal. And I want to draw you a little sketch of what that means. Transverse waves. So imagine holding a string. You're holding a string tight. It's attached at the other end to something. And you shake that string. Shake it up and down. When you do that, you're going to create a pulse that travels in that string. Shake it up and down. Here's this pulse. It's going to travel along the string. And notice that this pulse has a velocity vector along the length of the string, but it has a displacement perpendicular. So the direction of the disturbance is up and down, whereas the direction of propagation is forward. We call this transverse. Now it's also possible to have another type of wave where the direction of the disturbance is the same as the direction of propagation. That's called a longitudinal wave. Displacements parallel to the direction of propagation. And a classic example of a longitudinal wave is a sound wave. So this one's a little harder to sketch, but I'll draw it for sound wave. Here's a loudspeaker. The speaker works by moving back and forth. Here's the air in the room. Those are all the air molecules, nitrogens and oxygens. When the speaker moves forward, it compresses the air that's next to it. Pushes those molecules closer together. So that compression then propagates outward from the speaker. And that is an example of a longitudinal wave, where the displacement of the medium of these molecules is in the same direction that is getting propagated. As opposed to transverse, where the displacement is perpendicular to the direction it's moving in. So transverse waves, let me give you some examples. Water waves. Waves on strings, like I drew. Some seismic waves. Electromagnetic waves are transverse, but they don't have a medium, so I won't include them here. Essentially, all solid materials can have transverse waves in them. And longitudinal waves, here's some examples. Sound is maybe the most common one. Some seismic waves can be longitudinal. And you can have longitudinal waves in springs as well. You can also have transverse waves in springs. So seismic waves in springs can be in both categories.